Hello guys, in this video we are going to discuss the solution of the problem modular exponentiation for large numbers. So let us look at the problem statement. The problem statement says that implement pow x to the power n modulo m function. In other words, for a given value of x, n and m, find x to the power n modulo m. So for instance, in the first example, we want to compute 3 to the power 2 modulo 4. And if we do that, the remainder we will obtain is 1, and that is what we are returning over here. In the second example, we want to compute 2 to the power 6 modulo 10. And if you compute that, the remainder we will obtain is 4, and that is what we are returning. So that's about the problem statement, folks. Now let us discuss the solution of this problem. So in order to solve this problem optimally, what we need to do is we need to compute x to the power n optimally. And the running time complexity to compute x to the power n, we can do this in order of log n time. Now let us discuss the algorithm on how to compute x to the power n in log n time. So for this, let us take few examples. So let us say we would like to compute 3 to the power 5. In order to compute 3 to the power 5 optimally, let us first represent 5 into binary format. So over here I am taking the exponentiation form and I am representing that in the binary format, and this is the binary representation of 5. So once we have represented exponentiation in its binary format, the computation of 3 to the power 5 becomes very easy. And how can we do that? Well, 3 to the power 5 is equals to 3 to the power 4 into 3 to the power 1. And that is how we are going to compute this optimally. Now this 3 to the power 4, how is this 4, from where this 4 is coming from? Well, this 4 and this 1 is coming from these position. Right? So if you see, this is essentially 2 to the power 0, this is 2 to the power 1, and this is 2 to the power 2. So this is 4, which is over here, and 2 to the power 0 is 1, which is over here. So the corresponding bit which is set to 1 in its binary format, those powers we are taking. Now let's take few more examples in order to understand this concept. So let us say this time we want to compute 5 to the power 25. So the first thing which we are going to do is we are going to represent 25 in its binary format. So the binary representation of 25 is 11, 00 and 1. So 5 to the power 25 can be written as, and let us write down the bits also. So this is my 0th bit, this is my first, second, third and fourth bit. So this simply means 5 to the power 16, 2 to the power 4 is 16 into 5 to the power 8 into 5 to the power 1. And if you add these powers, 16 plus 8 plus 1, that results into 25. So this is what we are going to do in order to compute exponentiation optimally. So now let us discuss the pseudocode for this implementation. So over here we want to perform exponentiation optimally, and x to the power n is what we want to compute. So what we are going to do is we will have a result variable which will hold the result of exponentiation, and initially the value is 1. Now we are going to iterate on n while n is greater than 0. So we are iterating on this part. Now what we are going to do is we are going to check whether the corresponding bit is set to 1 or not. So to do that we are going to perform n and 1, and if this is not equals to 0, that simply means that corresponding bit is set to 1, and in which case the result will be updated as result equals to result into x. We will now perform the exponentiation. So the exponentiation will be equals to x is equals to x into x. And once we have done that, then we want to iterate on the next value of, or the next bit in n. So in order to do that, what we are going to do is we are going to flush this bit out, and the way we will be able to flush this is by performing the right shift operation. So if we perform right shift by 1, then this becomes equals to 1 1 0 and 0. So let us do that. So this essentially n will be right flushed by 1. And in this way we will be able to perform the exponentiation, and towards the end we are going to return a result. Now let us do a dry run in order to understand this algorithm. So let us say we want to compute 5 to the power 25. So as from the above discussion we know this, that 5 to the power 25 is equals to 5 to the power 16 into 5 to the power 8 into 5 to the power 1, and the binary representation of 25 is 1 1 0 0 and 1. So this is in binary format. Now let us see how with this algorithm we will be able to compute this part. So the result will be equals to 1 initially, and we are going to iterate on n, and this is the value of n. So from this step we are checking whether the LSB equals to 1 or not. So as we can see, the LSB is equals to 1. So what we are going to do is we are going to update result in this fashion, which is equals to result into x. So the result will be equals to 5. Now after doing that, x is equals to x into x, which is equals to 5 square, and n will be shifted by 1. So now our n becomes equals to 1 1 0 0 in its binary format. Now again let us proceed forward. Over here the LSB is not equals to 0, so the result remains as it is, and x will be updated now. So x will becomes 5 to the power 4, and then we will right shift our n. So now n becomes equals to 1 1 0, repeating the same process. So the result will remain unaffected because the LSB equals to 0, and we will compute 5 into 5 to the power 4 into 5 to the power 4, which will becomes 5 to the power 8. After doing that, the n becomes equals to this. Now the LSB is equals to 1, because of which the result will be updated by result equals to 5 into 5 to the power 8, and then we will compute x equals to x into x, which is equals to 5 to the power 16, and n will be equals to this. After doing that, since the LSB equals to 1, so we are going to compute 5 to the power 16, and after doing so, n will be flushed out and our n will becomes equals to 0, and then the loop will break and the result will contains what we wanted to compute, which is result is equals to 5 to the power 16 into 5 to the power 8 into 5. And in this way we are able to compute the exponentiation optimally, and the running time complexity will be order of log n. Now folks, in the question it is mentioned that we want to perform the modular exponentiation. So in order to perform the modular exponentiation, all we have to do is we have to divide this, or we have to take the modulo with m, and let us say the modulo we want to do is m. Similarly over here when we are doing it, we will perform modular m, and in this way we will be able to perform modular exponentiation. So that's the whole algorithm folks. Now let us see how we have implemented this in Python. So the implementation is pretty much the same, which is over here, which is implementation of custom pow function, and we wanted to perform x to the power n modulo m. Over here few base cases. So if n is equals to 0, that simply means x to the power 0 equals to 1, in which case this will be 1 modulo m. Similarly, if x is equals to 1, then 1 to the power n will be equals to 1, because of which we are returning 1 modulo m. Now the custom pow function. So the result is equals to 1, and we are iterating on n while n is greater than 0. Now if the LSB is set to 1, then the result will be updated in this way, and we are computing the exponentiation and we are right shifting the n, and towards the end we are returning result. So that's the code folks. Now let us submit our solution. So our solution got accepted. That is all from this video folks. In case if you have any question or comment regarding this video, please feel free to use the comment section and I'll try to address them. Thank you.